Matter in motion. Section 1. Measuring motion. Key concept. Motion can be measured and described in many ways. If you look around, you will likely see something in motion. Your teacher may be walking across the room. Perhaps your friend is writing with a pencil. Even if you do not see anything moving, things are in motion all around you. Air particles are moving. Earth is circling the sun. And blood is flowing through your blood vessels. Motion and reference points. You may think that you only have to watch an object to tell that it is moving. But often, you are watching the object in relation to another object that appears to stay in place. The object that appears to stay in place is a reference point. When an object changes position over time relative to a reference point, the object is in motion. You can use a reference direction, such as north, south, east, west, up, or down, to describe the direction of an object's motion. Standard reference points. As Figure 1 shows, features on Earth's surface are often used as standard reference points for determining motion. Non-moving objects, such as trees and buildings, are also useful reference points. A moving object can be used as a reference point too. For example, suppose that a bird flies by the hot air balloon shown in Figure 1. Anyone in the balloon will see that the bird is changing position in relation to the moving balloon. Motion in a two-dimensional system. Figure 2 shows a two-dimensional system in which a sheet of paper is passed around a room. A grid can be used to describe motion in such a system. The reference point, Owen's desk, is at the origin, where the x-axis meets the y-axis. 4 reference directions are represented by the positive and negative directions on the axes. As the paper in Figure 2 moves toward the front of the room, the paper moves in the positive direction on the y-axis. As the paper moves to the right side of the room, it moves in the positive direction on the x-axis. As it moves toward the back of the room, the paper moves in the negative direction on the y-axis. Finally, as the paper moves to the left side of the room, it moves in the negative direction on the x-axis. Average speed. The speed of an object is the rate at which the object moves. The speed of an object is rarely constant. For example, the speed of each racer in Figure 3 varies during the race. So, it is useful to find the average speed of an object. Average speed is the total distance traveled divided by the total time taken. The following equation can be used to find average speed. Average speed equals total distance divided by total time. Suppose that it takes you 2 seconds to walk 4 meters down a hallway. You can use the equation above to find your average speed. 4 meters divided by 2 seconds, or 2 meters per second. The SI unit for speed is meters per second. Other units for speed include kilometers per hour, feet per second, and miles per hour. Making a graph showing speed. Speed can be shown on a graph of position versus time. On this kind of graph, position is a measure of the distance of an object from a reference point. The object's distance from the reference point in either the positive or negative direction is plotted on the y-axis. So, the y-axis expresses distance in units such as meters, centimeters, or kilometers. Time is plotted on the x-axis. Thus, the x-axis displays units such as seconds, minutes, or hours. On a graph of position versus time, The slope of the line is equal to the speed of the object. Recognizing speed on a graph. Suppose that you watched a dog walk beside a fence. The orange line in the graph in Figure 4 shows the total distance that the dog walked in 10 seconds. Notice that the dog did not walk the same distance each second. The distance varies because the speed is not constant. The dog walked slowly at first. Then it moved quickly for 1 second. The dog did not move for the next 3 seconds. During the last 4 seconds, the dog walked with a moderate speed. The dog's average speed can be calculated as follows. Average speed equals 7 meters divided by 10 seconds, which equals 0.7 meters per second. Suppose that the dog walked at a constant speed. The red line on the graph shows how far the dog must walk each second at that speed to cover the same distance covered earlier. The slope of this line is the average speed. Velocity. Direction matters. Suppose that 2 birds leave the same tree at the same time. They both fly at 10 kilometers per hour for 5 minutes, 12 kilometers per hour for 8 minutes, and 5 kilometers per hour for 10 minutes. Why don't they end up at the same place? Have you figured out the answer? The birds went in different directions. Their speeds were the same, but they had different velocities. Velocity is the speed of an object as well as the direction in which the object is moving. Speed versus velocity. The terms speed and velocity do not have the same meaning. Velocity must include a direction. If you say that an airplane's velocity is 600 kilometers per hour, you are not correct. But you can say that the airplane's velocity is 600 kilometers per hour south. Figure 5 shows an example of the difference between speed and velocity. Changing velocity. The velocity of an object is constant only if the speed and direction of the object do not change. So, constant velocity is always motion along a straight line. The velocity of an object changes if the object's speed, direction, or both change. For example, as a bus driving at 15 meters per second south speeds up to 20 meters per second south, its velocity changes. If the bus keeps moving at the same speed but changes direction to travel east, its velocity changes again. And if the bus slows down at the same time that it swerves north to avoid a cat, the velocity of the bus changes yet again. Table 1 shows other examples of velocity changes. Acceleration. The word accelerate is often used to mean speed up, but the word means something else in science. Acceleration is the rate at which velocity changes over time. The units for acceleration are the units for velocity divided by a unit for time. A common unit for acceleration is meters per second, which is also written as meters per second squared. Velocity changes if speed, direction, or both change. So, an object accelerates if its speed, direction, or both change. Figure 6 shows the acceleration of a person on a bicycle. The person is accelerating because his speed is increasing. An increase in speed is sometimes called positive acceleration. A decrease in speed is sometimes called negative acceleration or deceleration. Circular motion, continuous acceleration. You may be surprised to know that even when you are sitting still, you are accelerating. You may not seem to be changing speed or direction, but you are. You are moving in a circle as Earth rotates. An object moving in a circular motion is always changing direction. Therefore, the object's velocity is always changing. So, the object is accelerating. The acceleration that happens when an object moves at a constant speed in circular motion is known as centripetal acceleration. Centripetal acceleration happens as a Ferris wheel turns at an amusement park and as the moon orbits Earth. Figure 7 shows another example of centripetal acceleration. Recognizing acceleration on a graph. Acceleration can be shown on a graph of speed versus time. Suppose you are playing with a remote-controlled car. You push the lever on the remote to drive the car forward. The graph in Figure 8 shows the car's acceleration as the car moves east. For the first 5 seconds, the car moves faster and faster. You know that the car's acceleration is positive because the car's speed increases as time passes. You also know that the acceleration is changing because the line between 0 seconds and 5 seconds is not straight. For the next 2 seconds, the speed of the car is constant. So, the slope of the graph is 0, which means that the car is not accelerating, 0 meters per second per second. During the last 3 seconds, you let go of the lever, and the car slows down. The car's acceleration is negative because the speed of the car decreases as time passes.